can start.
Yeah, so welcome back. So for
Thank
the third
you.
session, we are having a lecture on the lightning events in the distribution system. So, sir, this is the third session. We can start.
Thank you very much for attending this afternoon class. This was just 1 hour. I will try to speak about protection against lightning, okay? And that are one of the events that may cause faults into the distribution network. In this course, we are not dealing with much about relays or protection, but at least we are dealing with something about the protection and the design of the lines in order to reduce the risk that is associated with this event, that is the lightning. I would like to start with a website also here, and that is this here, so we can try to do. That is a website of Indian about climate hazard, and there is a part other than extreme rainfalls, wind hazard, dust storm, and so on, that is related to lightning. And there is this map. It is, I mean, the data are 1998, 1013, no? So I don't know if there is something updated, but at least I found this. And it gives, I mean, the idea that not all the areas are affected by the lightning in the same way, but there are areas that are more affected than the others because of weather conditions, and also to orography, for example, mountains with respect to so plain area, and these numbers are the average lightning flashes per square kilometer per day, so per day. I would like to ask you if you know what is a lightning flash. Do you know what is a lightning flash? And what is the lightning event or stroke? Oh, it is due to the fact that lightning is a physical, we can say, phenomenon, in which we have the condition that creates the possibility. I will change the color. Probably it is this. Oh, perfect. Thank you so much. In which there is the cloud, the thunderstorm cloud, okay, and there are conditions in which there is a propagation of a channel, of a leader, they say, from the cloud to the ground in this way. This is very ionized path inside, so can be positive, can be negative, and so on. And at some point, I mean, there are also intra-cloud events, but we are not interested in this. We are interested on cloud-to-ground events. And at some point, for example, because of there is a structure, I will not change the color, this very high ionized path, for example, positive, but can also be negative. Both polarities are possible. Since there is this high charge near to the structure, also in the structure there is the creation of ionized path on the other way, and there is the possibility, the chance that these two connects. At that point there is the stroke, so this charge is equalized. So there is a return stroke. This is the current. Until now there is just the charge, but until now there is the current, a current wave shape that propagates from the structure, we can say from the ground, this is the ground, to the top at a speed that is a fraction of the speed of light, 1/3 of the speed of light, typically, no? Okay. This is called a stroke. But since the path is already ionized after the first stroke, then since the channel is already ionized, depending on the condition, you may have also after some times that the charge from the cloud follows the same path or practically the same path. Can be, for example, from that way to another structure nearby, no? And creates therefore another stroke, retro stroke. So retro stroke is indeed the event that we are interested in. We are not affecting much on the charge of the leader of the initial path in the atmosphere, but we are affected by the current that is flowing into in this path that can have a peak of above 100 kiloamps. The average, the median value is for those the events that are recorded is around 33 kiloamps. No? But we have events also that are above, not much above, but above 100 kms. And the typical front time for this lightning current, so the time to peak value, the time to peak, so the time from 0 to the maximum, so the maximum is the average, the median value is 3.3 microseconds. So you see very short and very a pulse. No? And for the same event, we may have one stroke, but also a second stroke, a third stroke. Oh, they are measured also more than 20, also more than 40, it depends. No? And all the total event of these strokes in the same channel, it is called a flash. So this is the difference between retro strokes or events and the flashes. Here are the flashes. So it means that these are not one stroke. They may be several, but they are in the same time window and in the same area that is considered to be ground. I do apologize. That is considered to be the same flash. So it is also some kind of definition. No? I define the flash as the collective events that are. There are sensors in various locations that are sensitive to these events, in particular to the electromagnetic field produced by the stroke. So they can evaluate the intensity of the stroke, but also can localize because of the several antennae, no? And they can make a triangular calculation, and so they can provide the location. So this is the so-called location lightning detection system. I done something wrong? No problem at all, because I would like to open another website, so in the way that is coming. coming, I can say. Good. So I would like to show to you that the maximum numbers that I can get here, it is about 0.18 flashes per square kilometer per day that are expected in some particular region in India. And if we multiply it by the number of the days per year, it is in the order, 18 multiplies by 100 multiplies by 3, probably 60, no? And I will show to you a map that is more updated, that gives instead the number of events, because it is from the company that mainly sells these antennas for the lightning location system, that is Visal, and has collected all the data for around the world and so on. So and you see that the numbers are much higher than those, but because they detect each stroke. So when they speak about event, it is each stroke that they can detect, even though in the usual maps they are collected in a flash. This has some relations with the protection, because we think that different strokes in one point, we try to avoid that the stroke is connected to the line conductor, or so probably many strokes in the same point are not equal to different events. It is just the same event, because the time window, it is on the order of few microseconds, no? Tens of microseconds. So it is of the order of the intervention of the protections that needs some interval in order to also open the circuit breaker and so on. So in globally. But for some cases, in particular for energy of the surge arrestor, you need to take into account that there is not only stroke, but there are 20 strokes in the flash. So it depends on the situation, on the total charge. Oh, no problem at all. Probably is my intervention on the website that creates this interference. I don't know. But I don't have any other website to show to you, so it is the last. Do you have any questions so far? Any curiosity about lightning or events? Or? Yeah. One of the things that are mostly affecting me when we are dealing with lightning and so on is that in the lab, we say that the current waveform of the lightning strikes, it is a 2D exponential waveform, very, very clean, and this is just because of the limitation, the capabilities of the high voltage generators that we have in the lab that allows, they are designed in order to provide a certain waveform. So in general, I design this waveform, no, like the lightning current. But if you actually measure the current at the channel base of the lightning, or the current can be, the waveform is a natural event, so can be varied. You can also have some waveforms that have two peaks. No, or very different. No, so it is. Our idea that the pulse of the current of the lightning at the channel base is just a two exponential function. It is just because our generators in the voltage lab, they reproduce this behavior. But in the reality, I mean, the waveform can be very different. Indeed, it is not so easy to measure, indeed, the current, because the current, we said, that can be also several tens of kiloamps. So in general, we protect us, not put the instrument there in order to measure the current. So the equipment, it is quite sophisticated in order to survive, to measure the current and so on. Most of the measurements for the currents and the statistics that you see in the standards, the average time to peak, the maximum peak of the current, what is the positive or negative, and so on, they are derived by measurements from towers. So there are also, I don't know, Toronto, there is a tower also. There are also many towers in the city. So in many of them, there are some equipment in order to measure this current, and this provides the statistics for the actual behavior, waveform of the current to the ground. Yeah.
Current transformer and PT potential transformer.
Yes, and this is Rogowski coil, for example. It is one of the tools that are needed. Yeah, in order to have this recorded, this behavior, and having the statistics. Good, very good. So I can try. I hope not to disturb. Oh, this is another thing. Oh, this is the website of the Vaisala, the manufacturer of these antennas for the lightning location system, and provides the number of events per square kilometer per year. You see, it goes from 1 to 100, and you see, I can start with the region of Italy, but we can go also in India, and you see that, I don't know if we have here in this part, I don't know, probably here are 8 events per square kilometer per year, here 16 events per square kilometer, 32, and then 48, and then there are also some spots above 80 events per square kilometer per year. You see that it is varying. I mean, these maps are, very specific for all these regions. And you see here also with a difference of some, I don't know how many kilometers, probably tens of kilometers, probably 100 kilometers. You go from 8 events per square kilometer per year to the 16 events per square kilometer per year. So it is very local, this behavior, and therefore this suggests the idea that not the same rules, not the same protection rules for all the regions can be applied, because in some regions there are no lightning, so it is not useful to install surge arrestor everywhere. It is just a cost. And in other regions, this may be not sufficient, so you need also to install something more than what. So it is very localized and very designed. So the idea of behind our study is to calculate, and we can also move here, we focus on the calculation of the lightning performance of a distribution network. Lightning performance, it means that number of faults due to lightning, no? so faults into the network per year. So we can say probability to have or estimate to have a fault per year in that network. For this, we use a Monte Carlo procedure. So several events are created, taking into account the number of events expected in that region, and for each event we calculate if the voltage, the over voltage, induced or caused into the network is above the insulation threshold of the insulators and so on. So the capability for the insulation of the system to sustain the over voltage. And I would like also to show to you a case, a specific case in particular for a line in which there are different circuits at different voltage. So it is called a multi-circuit high voltage, medium voltage overhead. But I can start with just this picture in which there is just a nomenclature. So you see here overhead lines. In general, we are focused on overhead lines. Underground cables are already protected by the ground and so on in large part. And then you see the conductors in some lines, not in all. It is also installed this wire above that is connected to ground, so the shield wire, and these devices are the surge arrestor. So if the voltage increases too much with respect to the rated voltage, they provide a low impedance path to ground, to the lightning current, and then it is the transformer. So we can distinguish between direct strikes in which there is a connection of the leader, and so there is the strike directly to the conductors, and this is in general associated with a shielding failure. So we are expecting in general that the direct strikes is to the shield wire and or another structure nearby, and if it is connected directly to the conductor, it is called shield failure. And then there is another event in which there is a direct strikes, but the direct strikes to the shield wire. In general, we can say, okay, there is a strike to the shield wire, so there are no problems. It is not true for all the cases, because in some cases the current is so high. You can think about 100 km, that this current is flowing to ground, but the impedance of the pole and the impedance of the grounding is not zero. So you can multiply this 100 kiloamps for the typical grounding resistance of the poles. I don't know which is the grounding resistance. 20 ohms? 10 ohms? Or you can multiply it is the megavolt. So you see that this is a line of 20 kilovolt, or 11 kilovolt. There is no insulation that can sustain the megavolt. So you have this kind of problem, the back flashover. So there is a flash from the pole to the line conductors because of the high voltage that is reached by the pole when it is subjected to a very high current. But there is another effect that is the fact that we can have indirect strikes, so strikes not to the structure directly, but on the vicinity. For example, there is a line with buildings and the strikes is on the buildings around the line or in the terrain around, because there is a tree, no, nearby to the line. So in this case, the current is not flowing directly in the line conductors, but this very intensive pulse, no, of current is creating a pulse also associated with the electromagnetic field, the so-called lamp lightning electromagnetic pulse. And this pulse electromagnetic is coupling with the line conductors of the line, so induce voltages. So this is mainly the picture. Do you have any questions so far with this picture? So this is the lamp. So what is the lighting performance of distribution lines? In general, we speak about a diagram in which in the x-axis we put the insulation level in kilovolt for the line insulation. In the y-axis, the number of induced voltage with magnitude exceeding the value in abscissa. So the number of events that creates an overvoltage larger than the insulation level of the line. In order to minimize the number of annual flashover to lightning, including indirect events, that a distribution overhead line may experience. And of course, is as a function of insulation level, line construction design, ground flash density. So there are some standards, and I put here the classical one, the 1410 guide for improving the lighting performance of electric power overhead distribution lines, and also this document that is from SIGRE, protection of medium voltage and low voltage network. The typical figures that are there, therefore, are like this. In the here, it is the critical flashover over voltage, so practically the insulation level inside the line. Here there are the flashovers, and here are the curves associated with the conductivity of the ground, and in particular for induced. And you see that this is for ideal ground, this is for conductivity of 10 millisiemens per meter, and this is the ground conductivity for 1 millisiemens per meter. Okay. Do you see that by decreasing the conductivity of the ground, in general, we have this effect that the curve is shifting in the upper position. So it means that the number of events for a specific insulation level of the line, the lower the conductivity of the ground, the higher is the number of events per 100 kilometers per year. This is expected for just a straight line. The number of events increases. This is due practically because there is an enhancement of the effect of the lamp when it propagates on a terrain with a lower conductivity, lossy ground. I need to go, but it is okay. Monte Carlo method, I would like just to review the Monte Carlo method. A large number of events or lighting events is randomly generated, position, the current, the characteristic of the lightning current, and then the events are assumed to follow the probability is log normal provided by the standards, and for all the events we distinguish between indirect lightning and direct lightning. In general, if it is a direct lightning, the important aspect is the current. If it is indirect lighting, the important aspect is that the electromagnetic pulse that is created by this stroke that propagates along the channel. And for each event, we calculate the maximum voltage into the line, and we count the number of voltages that are above the insulation level with respect to the total number of events. We need to consider the area around the line and the ground flash density, that is the number of flashes per square kilometer per year in this, or strokes, in this area.
A is 1 square kilometer.
A is the area around the installation. So I can show to you directly what is the A and then come back. For example, this is a calculation for a single line. So you can imagine that this, for example, is a line. So this is a top view. This is the position of the line. And we create many events around the line. Obviously, there is one side and the other side. But since it is symmetrical, we can consider just for the calculation one side. So we take into account this area, for example, 2 kilometers from the line, expecting that one event that is hitting the ground behind 2 kilometers does not affect our lines, and we create all these events in this area, and we distinguish between the red events, so the events that are direct events to the lines conductors, and the events that are hitting the ground around. Here we expect that the line, we assume that the line is in the plain ground. And but this creates a lot of the events that are not dangerous at all. So the fault, it is a rare events. So you need, in the Monte Carlo simulation, you need to increase a lot the number of events that you need to calculate. So the calculation takes a lot of time because there are many events that are not dangerous at all, and because they are too far or because the current is too low. And so we adopt this stratified sampling technique. So it means that we tend to reduce the number of calculations in order to obtain the same quality of the result, and the quality can be estimated by the relative error for 95% confidence intervals. So the intervals you see here in this equation, that this P is the estimation of the probability, so number of events that creates problems, so over voltages behind the insulation level with respect to the total number. Since this P is low, in this equation, since it is in the important effect is in the denominator, Cp tends to be high. So we need to apply a technique in order to reduce the event. And this technique, stratified technique, it is allows this significant computational times reduction. You see 75%, because you see that we are not spreading all the events in an homogeneous way. We have some events also far away, but most of the events are considered nearby to the line. So we can concentrate this, and the stratified event method, it is a method that allows you to concentrate the events where it is important, it is needed, with a sound logic based on the variance of the local estimator that is recursively updated until in each subdomain we divide the area in subdomains, in which in each subdomain the desired estimation error is reached. This is also shown here in this figure, in which we have also the surge arrestor. So there is a line in which periodically in some poles there is a surge arrestor installed. So you see the stratified technique concentrates the events far away from the surge arrestor, near to the line, but far away surge arrestor. We are not considering many events here because these events are not so important, because since they are near to where there is the surge arrestor installed, then they cannot create an important overvoltage into the line. There is also a table here that indicates the time saved, and this is also repeated for a more complex configuration, not a straight line. And these diagrams above indicates the advantages. Here just confirm that if you use the standard Monte Carlo method and the stratified ones, you obtain the same curves, because these are exactly the same. And here you can see that in the x-axis there is the number of events, and you see that by using this stratified technique, by increasing the number, the error or the confidence interval decreases with respect to the other. So this is the computational advantage for this. I would like to mention just for 1 minute how they are calculated, the induced voltages into the line. So you see here that there is the classical equations of the lines, the transmission lines. You can recognize the voltage, the inductance per unit length, and also the effect of the ground. And but there is something more in these equations that are not typically shown in the books of transmission lines, that are these components here, these two, that are also represented in the usual equivalent circuit of a line. There is the inductance per unit length, the impedance that takes into account also the ground, the shunt capacitance of the line, but there are no these things in green here and also in blue here. These are the effect of the lightning electromagnetic impulse that is coupled with the line conductors. So the equation of the lines is modified in order to take into account the induced effect caused by the electromagnetic field of the lightning. So these are the horizontal and vertical component of the electric field that is associated with the intensity and the characteristic of the lightning current that we are considering, and also the position of this lightning event with respect to our line. Where the ground resistivity plays a role in this part, but specifically in this component, the horizontal component of the electric field. And this is the cause of the increasing of the overvoltage because of the low ground conductivity. Oh, we have, for this calculation, we are, this is just a simple case of a calculation. This is a straight line, this is a stroke location, so where there is the lightning, and we are calculating the overvoltages in these 3 points. So you see here the voltage in the first point near to the stroke location, that is the I, and then lower and then lower. This is the case for the lossless ground, so with the conductivity very high, so very high conductivity. And this is the same calculation for the same event with the same characteristic of the current in the lightning channel, but with a lossy ground. So it is 10 millisiemens per meter, so reduces, so this is lossy. So you see that the voltage here is higher than here, and the voltages are higher, and moreover there is this effect of this peak. So if we calculate the voltage very, very, very far, this peak increasingly is down, is down, is down. So you can also have the maximum over voltage very far from the lightning point, so not in the near to the stroke location. In order to do the calculation for a network, we need a lot of components, not only overhead lines, but also various components. So we have implemented the model of the line illuminated by the electromagnetic field created by the lightning in electromagnetic transient program. That is the typical simulation environment for transients, and so we can use all the components, surge arrestor and so on, available in the library of EMTP. And this is also the our LIOV module, that is the module of the line illuminated by the lightning. Just a few words about direct lightning events. We take into account the insulation flashovers by this equation that represent the possibility for the insulation to not sustain the overvoltage during the time. And also we can take into account the fact that when there is the lightning current in the grounding, there is an effect of soil ionization that is in general a benefit because it decreases the resistance of the grounding. So I would like to show just this calculation for a real distribution network in Brazil. I will not go again in the website. Yeah. Yeah. Yes, so this should...
but the probability of failure of the surge arrestor is very high.
Yes, sir.
Then in that case, will the Monte Carlo method will give the accurate results?
Yes, sir, because if with the Monte Carlo method we can calculate the current that is flowing into the surge arrestor and the energy. So we can have a statistics of the energy associated with the intervention of the surge arrestor. So the higher the energy, probably the higher is the probability that one of the surge arrestor will be in failure. No? But the problem of the surge arrestor is that they are affected by faults and therefore indeed this idea was behind this project for this network of the real distribution network in Brazil, because they wanted to limit the number of surge arresters there in order to decrease the maintenance cost of replacement and also the risk that some of those are not working properly.
Sir, the failure rate is high just because of the zinc oxide inside the surge arrestor or any other specific?
I have not understood. Can you repeat?
Sir, I'm saying the zinc oxide we are using inside the surge arrestor.
Yeah.
Because of that, the failure rate of the surge arrestor is high.
Yeah.
Or some other specific reason. I want to say that is there any specific reason in distribution system and in transmission system, or the same reason of failure is there?
Probably the same. The technology in transmission system can be a little bit different. They may use also gap surge arrestor that may be less affected by something, no? So, but more or less the technology is similar in transmission and distribution, and also the same idea that reducing the number of surge arresters may be useful in order to reduce the cost and reduce these effects. So this was also the idea here for the for this network in Brazil. It is in the southern part of Brazil, so there are a lot of lightning events during the year, so the number of flashes per year is quite high. And so it is in this region, so you see also the network here. And we take calculation procedure. The topology of the network is extracted from the geographic information system, and a procedure automatically discretizes each line to meet the finite difference FTTD requirements. That is the technique, the numerical technique that we use in order to calculate the transient in the line. So we discretize the line in 5 meters in general. And then we built the model in the EMTP software, and we calculated the statistics, so the number of events that are causing problems. And the idea is to calculate the mean time between failure for each medium voltage, low voltage transformer. If the mean time between failure is low, it means that there are too much problems in that area, and therefore it gives an indication where to put the surge arrestor or increase the protection in the area. And this is just the figure. Yeah.
This low means what is the threshold to say that this is low or this is high?
Yes, we can see just the results here. Oh, I'm coming. Yes, for example, you see that in a part of this area, I need to say here, for example, there is a time between failure in years, that is 200 years, 460 years, 200 years. Yeah, so it means that this area is very well protected. There are parts of this that in which it is just 26 year, 34 years, and 47 years here. So it means that you might expect in some year, a problem. So by this idea that the lower the number, the increased problems, you can see an area in which without including additional surge arrestor, the expected number of events, so the time between failure, is so long that is not, useful to put a surge arrestor there. And there are other parts of the network in which an installation of the surge arrestor may be improved, or at least the typical idea of this distribution system network operating, the surge arrestor installed in a transformer and in the others, so they are helping each other. So it is an area that is much more protected than an area in which there are very few laterals, few lines. So putting a surge arrestor there is very important. I can also go back just to show to you the procedure, that is the scheme of the network, the generation of all the events, red and blue, that we have seen before. And then this is the time domain simulation. This is the software environment, EMTP, with the lines and the various components. And these are just the characteristics of the poles that are included, and just an example of the overvoltage that are calculated in the observation points. Another thing that we have considered is the fact that in many urban areas the lines are not in the playing ground but are near to the buildings. So there is a shielding effect by the building. So the probability to have a problem into the line is lower than a line that is alone in the open ground. So how much this? There are two effects. One, the buildings or the trees may intercept several lightning flashes, but also the building with also the structure inside the iron and so on can reduce the effect of the lightning electromagnetic pulse. So these two effects are represented here with the shielding and the lamp attenuation. In general, for the shielding, IEEE provides this table that shows here it is the distance of the building with respect to the line, and this is a coefficient, and that means that the protection of the building with respect to the line take into account the height of the building with respect to the line. This is for a 10i line. So a line with the conductors 10 meters from the ground. And these are the simulation of with the attenuation with a FEM simulation. And you see the decrease of the overvoltages, and this is also shown in the statistics. So you see the usual graph with the voltage here, the insulation level, the number of events that are exceeding the abscissa, and you see here without buildings, so these black lines that takes into account also direct events, these blue lines with the shielding only, and this red with the shielding also of the lightning electromagnetic impulse. So you see that for some of the insulation levels it is important to consider also this in order to decrease this number. And this is also for a line with both sides, so buildings in the both sides. I promise, do you have any questions so far? So for the last 2 minutes, the last case that I mentioned to you at the beginning, there are cases in several countries, in several environments in which you need to save money and also save space. So there are some lines in which there is an high voltage line, and then installed in the same pole there is a medium voltage distribution line. For example, here was the case of 69 kilovolt or 138 kilovolt transmission line with a medium voltage 15 kilovolt installed in the same pole. With this compact, typically with this compact configuration. And there are also cases in which there is also a low voltage line. So in a project we have tried to estimate the lighting performance of this type of lines, that is a combination of lines, and we have seen that in general the medium voltage line is more protected when it is installed in the double circuit line with respect to the case in which there is the medium voltage line alone, so without. Because although the higher height of the transmission line collects more lightning, the shielding provided by the high voltage line conductors is, exceeding, at least in this case, and the effect. So the medium voltage line below, it results more protected. There is another effect that is very peculiar, is that along the line you can also have a low voltage installation, so transformers, medium voltage, low voltage transformer, and in some case, in some conditions, you have that the neutral of the low voltage line is affected by the effect. So this is the over voltage in the neutral on the other side of a medium voltage, low voltage transformers that is connected to the medium voltage line in the double circuit. This concludes this part. If you have any question, any idea? These are just some reference that you can see with a description that is more accurate and more detailed than this presentation. But I hope that I have given to you at least the overview of the problem and why we are doing these studies and what are the aim, the final aim. That is reducing the number of faults, at least caused by the lightning, no? In the regions that where there are lightning problems, no? And with the minimum cost, no? for the installation. I don't know if we can take a 5 minutes break, or we can go directly to the end of this first day, that is this laboratory, and try to start to use, some of you have installed, or no, they registered the Python Anywhere thing. It's good? It's up to you. Which is the time? I can try to start. So here it is written 15:30, so we are perfect on time. I was embarrassed to organize this laboratory because at the beginning with the Professor Mitra and so on, we were speaking about a laboratory, no, in order to do something in the computer, but which is the tool, no, and we can.
So we asked them to register to that link.
Yeah.
So did you register? Everybody have registered?
Oh, no. It is not mandatory. So I am opening also myself and try to.
Charger?
I don't know. I need to open. Okay. So we can try to do something very simple for today, but also the other days will be very simple, but this is just introductive to see what happens. So I need to see here.